hear me well? It's all good. Okay, let me just remove this. That's better. Right, yes. So in this talk, I'll be covering tau-lepton physics at Belle II. And yeah, just to give you a bit of a introduction, if you're not familiar. So the SuperKEKB accelerator is a asymmetric electron-positron collider located in Tsukuba, Japan. And it's a next generation B factory. So it collides electrons and positrons at or near the Upsilon 4s energy and produces lots of B meson pairs. This is why we call it a B factory. So as you can imagine, there's a very rich program of B physics. But there's also a broad program of tau physics. We hear about this today, and also other dark sector and low multiplicity physics. Now, going from its predecessor, KEKB, to the new SuperKEKB accelerator, it has a design 2 times the beam currents and also can reach a vertical beam spot size of 50 nanometers. We call this the nanobeam scheme, and this allows the detector to reach an unprecedented design luminosity of around 6 by 10 to the 35. And as you can imagine, this also means that the detector has to deal with higher beam backgrounds compared to Belle. Here you can see an example of a particular event to illustrate the larger backgrounds. But the Belle II detector represents a major upgrade from Belle to deal with this and improve detector performance in general. So here's a schematic diagram of the detector. And yeah, the main upgrades, there is now this 2-layer pixel detector with the first layer very close to the collision point, which improves a lot the vertexing. Then moving out, we also have this 4-layer silicon vertex detector, and then further out again, the central GIF chamber. These all provide, these are all together make up the tracking system for Belle II. Then we have the particle ID system, so the top and the new A-rich for KPI separation in particular, and the electromagnetic calorimeter, and also furthest out KLM, so K-long and muon detector. And also there's an improved trigger, which is particularly important for low multiplicity physics, like tau physics, which we'll see later, and yeah, faster electronics in general. Here I summarize the current status of the performance to date. So this plot here on the left shows the total integrated weekly luminosity for Belle II as a function of time, so as a function of the year. And you can see we had from 2019 up until around the middle of 2022, we had run 1, and this was followed by a long shutdown where we rejuvenated the detector, including the replacement of this innermost pixel detector. And then we are now currently in this run 2 period, which is ongoing, and we're in a little break now, but we plan to resume data taking in November. So during this whole period so far, we've recorded about 575 inverse femtobarns of data, E plus E minus collision data. And also we've set the world record for peak instantaneous luminosity. So this is a nice achievement. And this data set is split into 3 types based on the energy. So about 495 inverse femtobarns was recorded at Upsilon 4s, so our nominal working point. About 60, a bit below, mainly for background studies, and about 20 inverse femtobarns a bit above for some, in particular for some exotic hadron searches. And looking into the future, we're still in the very early stage, so we aim to collect 50 inverse attobarns over the full lifetime of the experiment. So this is 50 times the predecessor, Belle. Now, okay, most people think of Belle II as a B factory, but it's important to keep in mind that B factories are also tau factories. So the cross-section for tau pair production is very close to that of a B pair production. And in fact, as you can see summarized here are some particular tau physics highlights as a function of time, looking at the previous, the last generation B factory, so Belle and Barbar. And you can see they provided some important results over the last 2 decades. And over its lifetime, Belle II will deliver something like 46 billion tau pair events. So this is a huge sample, and it really is a unique opportunity to study tau physics with high precision. If you're not familiar, just to quickly say, in E plus E minus collisions, we mostly produce taus in pairs. So we call this tau pair production. and it's due to its mass, it's the only lepton, well, that's massive enough to decay into hadrons. So there's something like over 200 hadronic decay channels. These hadronic tau decays make up something like 65% of the total decays. Then there's also these leptonic decays to muons or electrons and two neutrinos, as you can see here. And here you can see sort of a full breakdown of the various leptonic and hadronic tau pair decays. So once produced, the two taus will decay into final states containing either one prong, so one charge track, or three, what we call three prong, three charge tracks or charge particles. And yeah, at Belle II, we mainly study these, what we call the 3x1 prong topology, where we split the event according to this thrust axis. You can think of this as sort of the direction of maximum elongation of the event, kind of like this. And in one hemisphere, in these 3x1 prong events, we have a three-prong decay with three charged particles, and in the other, the one prong, and they tend to be kind of back to back. And we also have the case where we have 1x1, where we have a one-prong decay, so both taus decaying into one charged particle. Here I just pick a particular event in real data. So this is a tau pair candidate event. And you can see here we're looking in the azimuthal plane, and you see here sort of on one side we have three charged tracks, most likely three charged pions, and sort of in the other hemisphere we have the one prong decay, and we have quite some activity in the KLM. So this is most likely a muon, and then the other tau goes to 3 pi's, just to illustrate with one event. Now, tau pair events tend to have a low multiplicity, so they typically can sit quite close to our trigger thresholds, both the hardware-based level 1 and the software-based higher level trigger. And so, and the two main triggers for tau physics are those that use information from the central drift chamber and the electromagnetic calorimeter. And there are several triggers that are unique to Belle II. So, for example, we have these long plus short track triggers, which, as you can see here, going from blue to orange, can give some quite improved efficiency, particular in the end cap regions. And also we have this unprescaled 1 GeV ECL energy threshold trigger, which you can see it has very high efficiency above this plateau at around 1 GeV for taus. And there's also quite a few ECL cluster topology triggers, which are particularly important for these lepton-flavour violating channels, which I'll describe later, that give quite a high efficiency in the region we're interested in. So yeah, although we have less data currently than Belle, the previous experiment, with these kinds of new triggers, it opens up some new tau physics opportunities at Belle II. Just briefly a bit about background suppression, sort of the basics of the tau pair event kinematics. So we're mainly trying to suppress QQ bar and bar backgrounds. They're not the only ones, but these are usually the main ones. And we typically take advantage of the fact that in this the thrust value, so we take this thrust vector, so the direction of kind of maximum elongation of the event, and then we project and sum up, and we have this thrust value. And as you can see, these tau pair events in blue have relatively mild deviation of the tau pair particles from this primary trajectory of the thrust axis. So we can sort of require this to be large to suppress QQ bar, but not too large, which helps us suppress, in particular, bar. Another very useful thing in tau physics is the fact that we have neutrinos in the events. So we look at variables like the sum of visible energy, and you can see that we can measure this quite well. So in E plus E minus data, we have precise determination of this missing energy, and this can also give us a handle to suppress bar and also QQ bar backgrounds. And many variables, not only these, but many others, are typically these days used to train machine learning techniques to help reduce these backgrounds while maintaining a high signal efficiency. Regarding the overall tau physics program of Belle II, so it's roughly split into two sort of cases. So the first is precision standard model measurements. So here we're sort of looking for indirect hints of some new physics, potentially, and some deviations in these standard model properties. These include like the tau property, so the mass, lifetime, tests of lepton-flavour universality, CP violation, and many others. And here, I mean, you can see, we'll come to these later, but we have these world's best measurements of the tau mass and EMU universality. And these are often systematically limited measurements. So yeah, they're often sub-percent measurements, and we need a good handle on systematic uncertainties to deliver world-leading results. Then we have many kinds of searches for rare or forbidden processes, mainly lepton-flavour violating processes. So here, this is sort of a direct, this would be a direct observation of something. If we saw something, it would be an unambiguous sign of new physics. So in these kinds of searches, there's often very little background, and we need to be smart to beat Belle with only half the data. So we use sort of more inclusive reconstruction techniques. We'll see some examples of this later. And we use machine learning techniques as well to keep backgrounds low while increasing the efficiencies. Okay, so into the first sort of class of measurements, these precision standard model measurements. So the first is the tau mass. So the masses and lifetimes are fundamental properties of the standard model. It's important we measure these precisely. And as you can see here, well, prior to Belle II at least, the uncertainties of these are significantly larger than that of muons and electrons. And these are important for these various tests of lepton-flavour universality. This is this usual canonical plot showing the branching ratio of the leptonic decay to the lifetime. So in this analysis, we look at these 3x1 prong events, which I mentioned earlier. And we access the tau mass by looking at this variable we call the pseudomass, which is reconstructed in this way here. And it's it tends to be below the tau mass, excluding some ISR effects. But it has this threshold-like behavior near the tau mass, as you can see here. So this is what the distribution typically looks like. Then if we zoom in this region, you can see near the tau mass, we have this threshold with some smearing due to detector resolution effects and some tails due to ISR. Then what we do is we fit this endpoint distribution with an empirical function in this region to then extract the tau mass. And as you can imagine, this is really a systematic limited measurement where we need to keep systematics under control, and a lot of work went into this within Belle II. In particular, this is this pseudomass. We want to make sure we have this beam energy calibrated well. So we measure beam energy calibration, correction factors, and systematics, and we calibrate this with BMEs on hadronic decays. And we also have an alternative method using Upsilon fluorescent line shapes to get this value. Here you can see as a function of time, this measured corrected collision energy, beam energy is a function of time. So we measure this quite precisely. Another thing where a lot of work had to go into was in the measurement of the momentum scale correction factors. So with tracks, we need to make sure we understand the momentum and the interaction, and we make sure we have the understanding of the magnetic field correct. And for this, we had many dedicated studies looking at corrections, in particular with d to k pi events, where you can see after we correct these, after we apply these momentum scale corrections, shown here in red, we have very good agreement with the PDG for the D mass as a function of this cos theta. And these are the two dominant systematics. And we were able to bring these down quite significantly compared to what was in the past. And this allowed us to perform this measurement on the part of the on-resonance run 1 data and achieve the most precise measurement of the tau lepton mass to date. So here you can see this final pseudomass distribution with the threshold-like behavior. And then we do the fit, we extract this value for the tau mass, which is the most precise from a single experiment to date. And this really demonstrates the high precision capability of Belle II. Another important test is of lepton-flavour universality. So if you're not familiar, this states that the couplings of the leptons to the W bosons is sort of flavor independent. And if you want to test this symmetry with taus, it's quite a simple test. In principle, it's quite a simple test. You have to compare the rates of tau to nu to tau to e in this ratio we call R mu. And prior to the Belle II results, some global fits indicated some relatively mild 2 sigma tension with the standard model. And yeah, one could imagine some new physics could potentially enter this kind of measurement. Like like a lepton-flavour violating neutral currents or light Z prime, something like this. And so, yes, I mean, we're interested to see if this tension will increase with more precision on RMU. And here, I would say only Belle II can really provide answers, at least for the foreseeable future. Now, this study used the full on-resonance run-1 data, and it considers this one-by-one prong topology, where we focus on the row tag. So we have this row going to a charged pion and a neutral pion. And this has a large branching fraction and relatively low backgrounds, and one important thing has a high trigger efficiency due to this, particularly due to this pi 0. We restrict our events really to the barrel region and a particular momentum region to ensure that we have the most precise understanding of the PID, so keeping the particle ID systematics, which are the dominant systematics, under control. And then we have some simple rectangular cuts to suppress backgrounds, and we train a BDT to perform the final background suppression. Here you can see a plot of the BDT neural network, not BDT. So this is the neural network output. And here you can see the muon momentum and electron momentum distribution after all the selections, data versus Monte Carlo, before we perform our fit. Regarding the fit, so for performing this extraction of this RMU quantity, we do a bin the maximum likelihood fit using the PyHF library in bins of this lepton momenta. And then here you can see, for example, the post-fit distribution. So we have 3 templates: the signal decays, then the backgrounds where we actually reconstruct the correct lepton on the signal side, and where we don't. As you can see, backgrounds are quite low in the end, and we have good agreement between data and Monte Carlo. And yeah, before we actually unblinded this result, we performed many checks in different subregions of kinematic variables and momentum, polar angle, missing momentum, charge, and different kinds of PID cuts, many things. And you can see, whatever subregion we look at, we get good agreement in the measured values of RMU. And so, yes, this is a systematically limited measurement. You can see the table of systematics here. The dominant systematics comes from charged particle ID, as you might imagine. And there was a lot of work in Belle II to get these under control. And yes, we have many different control modes to study and measure this. And this was a big effort to get both the efficiency and misidentification rates well understood, and the systematics under control. And with this, we measured the world's most precise test of LFU in tau decays from a single measurement. And as you can see here, it's consistent with the standard model at the 1.4 sigma level. And yes, we're working on a second paper that should be coming soon. So I'm working with a student on this, where we'll perform measurement of the same quantity, but looking instead at the 3pi1 prong topology, which is more cleaner events, potentially lower reduced systematics. And also we want to potentially also measure the absolute branching fractions for these leptonic decays. I would say the next precision challenge for Belle II is the tau lifetime. So you can see here, I mean, we can relate the proper decay time to the flight distance and momentum in the lab frame like this. So we want to measure these two quantities. And so what we can do at Belle II is reconstruct the 3-prong decay like this and estimate the momentum of the tau using the decay products. So the fact that at Belle II we have this nanobeam scheme, so this tiny beam spot size near the IP, we can estimate this production vertex as the intersection of the momentum direction and this vertical plane of the interaction point. So this kind of technique is really only possible at Belle II. And this allows us to use, for the first time, the 1/3 prong topology to measure this tau lifetime. In the past, like at Belle, it was only possible with 3/3 prong events. But here, using 1/3, we have something like 5 times higher efficiency, and the 2 times better proper decay time resolution. We have the PXT. Here you can see, for example, this proper decay time distribution in Monte Carlo. So yes, this is something we're working on now, and Belle II should be able to deliver a world-leading measurement of the tau lifetime with the current data. Another interesting measurement is that of CP violation and tau decay short pi nu decays with some number of neutral pi zeros. So yes, you can get CP violation in the kaon sector in these decays. So in the standard model, this has some non-zero decay rate asymmetry. This is the standard model prediction. It's well understood. But yeah, over a decade ago, Barber made some measurement where they observed an almost 3 sigma deviation from the standard model. So yes, the tau physics community is very much looking forward to an updated measurement of this quantity from Belle II. So this is another priority. Okay, looking further to the future. So at the ESPPU symposium in June, we presented some projections for precision tau measurements at Belle II. So the mass, lifetime, and LFU, leptonic branching fractions, the usual kinds of things. And some assumptions of systematics went into this, which are quite reasonable. For example, some things were simply scale with statistics. Other things, we assume the factor of 2 improvement, which is actually some other systematics, we assume the factor of 2 improvement, which is actually a bit conservative, I would say. We're almost there for some of the leading systematics. So I think these are relatively conservative projections. And here you can see where we are now and where we expect to be with something like 10 inverse attobans of data. And then there's the comparison to the eventually what could be measured at the FCCEE at CERN, which is at this central point here. Okay, now moving on to the next topic. This is searches for forbidden tau decays. And these are mainly lepton-flavour violating tau decays. So in the standard model, these kinds of lepton-flavour violating decays with charged leptons can occur through neutrino oscillations like this, but these are highly suppressed to something like the 4th power of the small neutrino masses. So they're very small, they're immeasurably small, so we wouldn't be able to measure this. But if we did see something at Belle II, this would then be some clear indication of new physics, so something else entering these loops. And this could be many things. Here's some examples for one of these decay modes, but they can typically enhance these rates to something like the 10 to the -8 to 10 to the -10 level, which is actually just below our current experimental sensitivity. So this is quite exciting. Here you can see that the mu to E transitions are already very well constrained by experiments like MEG, but the tau to E or tau to mu transitions have much weaker upper limits. And here B factories really provide the most stringent constraints. And actually, Belle II is already delivering some world-leading results, and we'll see some examples of this in the coming slides. So the first is this search for the lepton-flavour violating tau to 3 muon decay. This is one of these so-called golden channels for tau LFV at Belle II. And this is motivated by several new physics models. I mean, you can imagine there could be some new Z prime which enters here, or some charged Higgs models, or other things. And one thing we did at Belle II, which is new, is we looked at an untagged approach. So we didn't pick some particular 1-prong or 3-prong tag in one of the tau decays. We looked at completely inclusively, and this allowed us to was one of the contributing factors of achieving a more precise result in Belle with less data. We also trained the BDT classifier to suppress the QQ bar background. And these two things combined gave us something like a 3 times better efficiency with respect to Belle. And the idea of this analysis is that you then do some sort of cut and count in this elliptical signal region in this 3 muon mass by delta E. So the 3 muon energy subtract minus the beam energy shown here, where, as you can imagine, the signal will sit at the tau mass and 0 with some smearing due to resolution and some FSR, ISR tails. And actually, in this region, after all selections, we observed one event, which you can see here, which is consistent with the background expectation of 0.5. And we set the world's best upper limits with using about 424 inverse femtobarns of data. Then this analysis was extended into 5 more modes. These modes have 1 electron and 2 leptons with different combinations of electrons and muons, as you can see here. Again, we use the same strategy for inclusive tagging. And again, we use BDT, boosted decision trees, to suppress the main backgrounds. In this case, mostly dilepton and 2-photon backgrounds. And here you can see in one of the channels sort of the distribution of signal and background before we apply this final selection on the BDT. And then we perform some signal extraction using an unbinned maximum likelihood fit on the mass distribution as shown here. This is one example, extrapolating the backgrounds in a data-driven way into the signal region. And actually, we don't observe any significant excess in this channel or any of the other 4 channels, and we set the most stringent upper limits in 4 of the 5 decay modes, as shown here. Another recent result from Belle II is in this search for the lepton-flavour violating tau to lepton K short. This can be interesting in particular for some leptoquark models. So you can imagine that if there did exist some leptoquarks, they could enhance this kind of decay mode in this kind of a way. Actually, another unique thing of this analysis is it was the first time we combined the Belle and Belle II data in a single analysis. And this uses here we had about 1.4 inverse femtobarn of data in total, attobarns of data in total. And the tag here is 1 prong. And then in the signal side, we use lepton ID to distinguish the various signal decays, and also on the tag side. And we reconstruct the K short from 2 charged pions, as you can imagine. Then we have various pre-selections dependent on what you actually have as the tag. The details aren't important. And again, we use a BDT to suppress the dominant QQ background in the end. We then do a cut and count in the usual way in an elliptical signal region in the mass versus delta E plane, where we extrapolate the backgrounds, as you can see here, from some sidebands in the mass into the signal region. So it's data-driven background estimation. And yes, here we set the world's best upper limits, so we don't observe a signal. And these upper limits are 3 times or 2 times more improved with respect to Belle, depending if you look at the electron or muon signal decay mode. Okay, another recent result from Belle II is the search for tau to lambda pi. So these kinds of decays violate lepton number and baryon number conservation, and this, can help. Is interesting to understand and explain the asymmetry of matter in the universe. Okay, and we reconstruct the lambdas from a proton or an antiproton and a pion, as shown here. And for background suppression, the 2 main things which give us the best background suppression is this requirement on the flight distance of the lambda. So these will be displaced vertices from the interaction point, and you can see you can suppress quite a lot of background by having just simply requiring that these are displaced. And we also applied a gradient BDT. Then, as you can see here, this is the output of that BDT to perform the final background suppression. And then again, we play the usual game. We look for some excess in an elliptical signal region in the mass and delta E plane, where in the end, we don't observe any events in our signal region in the data that we studied. And we set upper limits on these 2 decay modes, which are, again, the world's best. So this is another nice result. Okay, finally, on LFV decays, let me talk about the lepton-flavour violating decay tau to lepton alpha, where this lepton is either an electron or muon, and alpha is some invisible particle that we don't reconstruct. And this can be interesting. This alpha could, for example, be an axion-like particle, where you can see in this particular mass regime, Belle II is really the only experiment that can probe this mass region. So Belle II performed an analysis. This was actually the first tau physics result from Belle II on just 63 inverse femtobarns of data. So it looks at these 1/3 prong tau pair events again, and we reconstruct this 3-prong vertex to help suppress backgrounds, and we veto completely neutrals in these events, both pi zeros and photons, to really keep backgrounds under control. And yeah, this analysis was relatively straightforward. There's no, it was just a simple cut-based analysis. So a set of rectangular cuts to suppress background, like that on the thrust value or the mass of the three-prong decay. These selections gave us quite a high purity and also quite a high efficiency across the full alpha particle mass range. The idea of this analysis is that, you cannot really boost to this tau rest frame due to this undetected neutrinos. So we approximate this by boosting to this so-called pseudo rest frame under the assumption that this signal tau has an energy of half the beam and beam energy, and that, we assume that its momentum we take the momentum vector of the three-prong decay and flip it, and we assume that this is the momentum magnitude and direction of the signal decay. So what you're looking for is some two-body decay bump over the standard model three-body decay spectrum, as you can see here. So this is the standard model, data Monte Carlo, and then these are what you would expect for these lepton alpha two-body decay. You can see, particular for higher masses, our assumptions that we made are more valid, and we have a better, more pronounced bump. We then set limits on the ratio of this lepton alpha decay to that of the standard model. Setting the upper limits on this ratio allows for partial cancellation of the systematics, which is mainly coming from lepton identification. And yeah, here you can see the upper limits that were set in the electron channel and the muon channel. This is actually the result from Belle II. And recently there was a publication performing the same kind of measurement, but on the Belle data, which you can see here, which now has the world's best upper limits. And yes, there's actually a third paper in the works using a new method at Belle II. Here, one nice thing about this method is that you can perform this analysis not only on 1x3 prong decays, as was the case here, but also on 1x1 prong, which is very nice. And I won't go into the details here, but the idea is that we perform a two-dimensional fit in two new variables. So if you consider the full kinematics of the event and the various kinematical constraints, you have this one variable we call M min and the other M max. M min has an upper endpoint at the alpha mass squared, and M max has a lower endpoint at the alpha mass squared. So this is what it looks like for signal, and it's very different in the case for background. Okay, and yeah, sensitivity studies indicate that this combined with the combination of the two channels can at Belle II give us an order of magnitude improvement on the current upper limits. So this is something that we hope to have published soon. And then projecting further into the future, I mean, there are many of these different decay modes to study, various radiative, leptonic, semi-leptonic, and other kinds of decays. Actually, there's over 60 of these lepton-flavour violating modes that we want to study at Belle II. And yeah, this is a projection comparing sort of existing upper limits to what we can expect at Belle II with 5 and then eventually 50 inverse arrow bands. And you can see here's that Belle II can push these upper limits forward by at least one order of magnitude. These are also some results we recently presented at this ESPPU symposium, looking at these two golden channels, tau to 3 mu, and then also tau to mu and gamma, showing the expected upper limit as a function of time. And you can see certainly Belle II and also eventually this super tau charm factory will be able to set the best limits for the next roughly 20 years until eventually the Terra-Z experiments enter the game in the 2050s. Okay, if I have time, very briefly would like to just mention a bit about searches for sterile neutrinos with taus. Do I have time? This will take about maybe 5 minutes max.
Yes, Petar, that's fine.
Okay. Yeah, so as you know, neutrino masses can be incorporated into the standard model by introducing some sterile right-hander neutrinos. There is this, for example, new MSM model, which introduces 3 of these such particles, N1, N2, and 3. And these kinds of models are very nice. They can simultaneously explain the origin and smallness of the standard model neutrino masses. And you have some dark matter candidate as well, and it can help explain the baryon of symmetry in the universe. So this is nice. And yes, these heavy neutrinos or heavy neutral leptons, whatever you want to call them, they interact with the standard model through mixing. And then, you can have some long lifetime due to their small masses and small mixing. And if you look at the mixing of the heavy neutrinos with the standard model electron and muon neutrinos, if you looked at this equivalent kind of plot, they're already of some pretty strong constraints. But the constraints for mixing with the standard model tau neutrino are much weaker, as you can see here. So we have this whole region here we were interested in, and which we should be able to access, for example, at Belle and Belle II. Of course, in the future, there will be experiments like SHIP, June, and the FCCEE, which will enter the game. But yeah, those results are still many years away. So in the meantime, Belle and Belle II can deliver some important results. Okay, let me just quickly mention a recent result from Belle, which is nice, I think. So it uses the full Belle data set, and it looks at the scenario where the tau neutrino mixing is much larger than that of the muon and electron neutrinos. And it looks for some kind of long-lived heavy neutrino produced in these kinds of tau pair decays, which then decays via a weak neutral current, as you can see here. So this is what it would look like looking down the azimuthal plane. So you have some, you're looking basically for one of the taus decaying with a charged pion, and then some displaced vertex, so dimuon vertex in this case, which can be quite far away from the interaction point. And then you look in the full kinematics of the signal decay chain, and you have some twofold ambiguity in the mass, so m plus and m minus, okay? But yes, in the end, what we observe is a single event consistent with the background expectations from Belle. These are the upper limits that they were able to set for both Majorana and Dirac neutrinos. And actually, at Belle II, it's expected that we can push forward these constraints by 1 to 2 orders of magnitude, not only with more data, but also taking advantage of the improved vertex reconstruction at Belle II. So this is something which is also in the pipeline. Another handle of looking for sterile neutrinos at Belle II is not explicitly reconstructing a displaced vertex, but instead inferring the existence of some heavy neutrino in the by looking at just at the kinematics of these 3 pi nu tau decays. So here, basically, the 3 pi system would be recoiling against some heavy neutrino, and so you're looking for some this kind of a crescent-shaped endpoint in this mass in energy plane. So depending on the mass of this heavy neutrino, you have some crescent-shaped distortion of this endpoint. The nice thing about this is it's sort of much more model independent, but of course it requires a lot of statistics and excellent energy and mass resolution. So this should be possible at both Belle and Belle II. Actually, some sensitivity studies were performed. You can find details in this paper, and you can see that at Belle II, in this case with 1 inverse Arabin, we should be able to set some limits in this interesting region that so far hasn't been so well constrained. Okay, and that brings me to my summary. So yes, you can see Belle II is on target, certainly, to deliver the world's largest sample of tau pair events, and this has already and will enable a very broad and rich tau physics program. So here I list sort of the main achievements from Belle II in tau physics so far. So we have the world-leading measurements of the tau mass and the test on EMU universality, and the world's best upper limits on these 4 lepton-flavour violating decay modes that we saw. Then looking to the future, I think coming soon, we want to have the most precise measurement of the tau lifetime. We want to have this measurement of CPV in tau decays, and this new updated search for tau to lepton alpha, and also start going into these 50 plus other lepton-flavour violating modes that we want to look into. There's also some interesting analyses that aim to search for heavy neutrinos, in particular set constraints on the heavy neutrino mixing of the tau neutrino, and many more, which I didn't have time to cover today. Okay, so yeah, certainly there's exciting times ahead. Okay, that's all from me. Thanks.
Petar, thank you very much. We will open the floor to questions. Who would like to kick us off?
Maybe can I ask one question?
Go ahead.
So you mentioned that radiative decay, so it's a tau to mu gamma, tau to e gamma, I think was slide 22 or so. And so you mentioned that there is a new method to analyze it. Will you also reanalyze Bell data using the same method?
Are you referring to this method?
Oh no, I was with the tau to mu gamma, or so slide 22, I think was it. I think there you mentioned there that you so it was a 3 muon, but you mentioned there that there was a new so I mixed it up, but you mentioned there was some new method, or you had some new technique.
Yes. So I mean, I guess certainly the lessons we learned from tau to 3 muon and tau to E2L, that is the use of inclusive tagging and using more advanced machine learning techniques. These are certainly being explored for the updated measurement of tau to mu gamma. So yes, I mean this is really next on our to-do list, and yes, I mean I think we can expect something from Belle II in the near future, for sure. Yeah.
But will you use that same method to reanalyze the Bell data as well?
That's a good question. At the moment, no, it's purely a Belle II analysis, but certainly, I mean, there's not only going to be one result on tau to mu gamma for Belle II. So certainly I can imagine in one of the upcoming results, there will be probably some combination of Bell and Belle II data, similar to what we did with the tau to lepton K short analysis. Yeah. But not all the measurements will necessarily be with the combined Bell and Belle II data.
Yeah. Okay,
just to follow that up, that's partly because of the different trigger properties of the two experiments.
Totally, yeah.
So you may not be able to gain that much if you combine it, or it's a lot of work to basically.
It's a combination of both things. So the trigger certainly plays a role in well, depending on the K mode, and yes, also it makes things more complicated in terms of the analysis. So if Belle II alone cannot deliver a world-leading upper limit, then yes, one analysis can consider then including the Bell data. That's another strong motivation, as was the case in this analysis. Yeah.
Yeah. Thanks.
Other questions?
Can you return to the slide on the axion-like particle projection?
Sure. Yeah. You mean this one?
It was the one where you had the projected constraints. So yeah, I think you just went past it. So.
This one. Okay.
No, I think it's the next one. Yeah, this one.
Okay.
Yeah, no, there was a few details that I didn't quite get. So what for this plot on the right? What is he's plotting the symmetry breaking scale? What is the coupling that is being probed here?
Good question. I'm not sure exactly. Well, I mean, I think probably more details will be provided in the paper. But yes, I mean, basically, yes, in this mass regime, there was a original measurement quite old from Argus. And I think here, really, it's only a Belle II that can enter the game. Yeah. So, I mean, a Bell and Belle II, of course. So let's see. Yeah.
Yeah, I think the label in the top corner is suggesting there's some lepton couplings of some pattern that is being assumed.
Yeah, something like this.
Yeah. True, but it's not clear whether it's just the axial vector or also the vector coupling switched on for the flavor off diagonal terms.
Right. Yeah, I'm not sure on the details of that, but yes, there would have to be some assumptions. There was something there. Yes, I think so.
Are there further questions for Petar?
Maybe also with that axion search. So what is the dominant contribution to the width of that? Because of course it's a two-body decay. It's all experimental, I guess, experimental uncertainties, what sets the width.
Yes. So I guess basically it's these two assumptions. So one of them is this assumption that basically the tau gets the full energy or half the beam, which is not too bad. But then this one is not, I mean, it's an okay assumption is if the alpha mass is relatively large, but yeah, the assumption that this signal tau momentum goes as the negative of this combined 4 vectors of the tag 3-prong decay. I mean, you have to make some assumptions, right? And it's not the best, but it's okay. I think this one is this method is less sensitive to these kinds of assumptions, right? So yeah, I think in particular at lower alpha masses, you'll see some much more significant improvement going to this, where the assumptions sort of hold more steadily across the full alpha mass range. Yeah. This method was actually first done by Argus. So, but Belle II and Belle sort of followed the pre-existing method, making these assumptions. But I think here we expect to see some significant improvements in the upper limit. Yeah.
Okay, good. Thanks.
Just to not a question for me, but just to say it's really impressive to see these results arriving from Belle II after a long pause in results and tau. So it's nice to see, that there's a breadth of results arriving again. So great for the future.
Yes, it's nice. I agree.
People can stay on the line to chat with Petar if they like, but I might see if there are any final questions for the public part of the talk before I stop the recording. If not, well, look, let's thank Petar again for really a good overview and prospect of what we're going to get from what we have got and what we're going to get from Belle II in the future. Thanks very much.